All right, let's get started. So, quick announcement. So, just a reminder of the lab schedule. So this week is Lab 8. So Lab 8 is it's meant to sort of get you starting to work with data like the data that you will be seeing when you gather data for your final project. So it has the lecture component, which is sort of a video that you can get online, is divided up between data collection, which is sort of what practices you should go through when you actually go into your system and start taking the data. Input modeling, which is how do you start picking those models, which we'll talk about a little bit more today, and then an introduction to the input analyzer. And so I'll mention the input analyzer a bit today and in the next lecture, but there's sort of a full tutorial in Lab 8. So that's the tool that, at least for continuous distributions, will help you fit some of the most common distributions. I thought that Ali was going to post it, but I think there might have been a confusion. For the noon lab or the 12:15 lab, Ali is at Informs this week, along with a lot of the other IE faculty. So if you do go to the in-class portion for Wednesday at 12:15, if you can go to one of the other labs, either the morning or the afternoon, then that's one option. Otherwise, you can make an appointment with me if you need help with the lab. I think Ali said that he's also going to make extra time available on Friday after he's back. And so if you're in the Wednesday 12:15, then I think he said only a handful of people show up in person anyway, but feel free to go to either one of the other labs or make an appointment with me or with Ali if you need help, in-person help with the lab. So then next week, there's not a formal lab, but so we're kind of viewing it as an open lab. So that could mean you either come and visit with your TA if you need help with your input modeling, but the idea is we're sort of providing formal time for you to start gathering data with your groups. So the lab report for next week's lab, what we do at the normal time for a lab report, will be this input modeling report, which is a short report. The details are online, where you're going to give me basically a paragraph of the system that you're going to work on for your final project, and then you're going to tell me some of the interesting features of that system, and then show me some data that you've collected, as well as some models that you fit using the tools that we talk about this week, both in the lab and in the lectures. So this is an opportunity for you to practice this input modeling on the stuff that you're actually working on in the report. So it's kind of a coupled thing where it's both almost a proposal for your project as well as some data showing you've gone out and actually been working in the field with that system. And then after that, the next 2 weeks, we'll just have 2 normal labs. So basically, we'll be trying to build you up to the point where you could build basic but useful arena models and do the input modeling in arena so that you're ready for the final project. And then these last 2 labs, which you'll kind of do in parallel while you're doing your final project, you're going to be introduced to more advanced topics in arena, which may be useful for some of you, maybe not as useful for others, but it just helps provide a little more exposure to the additional things you can model inside arena. And then we'll have 2 other weeks before your presentation, which will be open labs, so that if you need help with your models, then we'll have time for you to be able to meet with us during the labs to help give you that debugging or whatever you need. So that's kind of the schedule going forward. So again, the final project is in the air. So hopefully you're starting to form your teams and submitting this names of team members assignment, which is due Friday of this week to Canvas. So that is there's nothing really required there other than the names of your team members and then a statement of which lab section, just confirming that everybody's presenting in. And so after you submit that, then I will go in and build your groups inside Canvas so that all of your future submissions will be group submissions, and then you'll be able to make use of any Canvas resources for groups. So that's the first deliverable, and like I said, about a week and a half after that is that input modeling report, which, if I remember right, I think we've got, it's about 1 to 2 pages. It's not meant to be long. It's just meant, again, to identify what system you're studying and then show us some data that you've taken that you view as inputs that you'll do some input modeling on. So we want to make sure that you're ready to kind of start your models. And so you'll have some stochastic models pictured that you can then use to implement that as you start building the thing in Arena. So that's kind of what's moving forward. separate from the final project, we've got these additional ICAs. So there's this G3 that's available, which covers mainly content from the next lecture, and then there's only 4 more ICAs before the final exam ICA. And then there's the second to last homework is out. It's 2 questions. And so that's 1 question on input modeling, the other one on output validation. And so this is actually due 2 weeks after Thursday. So it's formally assigned on Thursday, and then you'll have 2 weeks after that. And that means you'll have plenty of time to kind of marinate in the topics from this week, as well as get the topics from Lecture H, which will be more helpful for the second problem in this homework. Then after that, there's just 1 more homework, homework G2, which is an arena homework, and you'll again have about 2 weeks to do that one, and then that's the last homework. So keep thinking about your final projects. Again, make sure you're forming those teams. If you're having trouble forming those teams, there's the discussion boards. People have been posting whether they need members or whether they'd like to join groups. There's also 3 Google Docs spreadsheets, Google Sheets, I guess, that for each lab section where people have been adding their names to and taking their names off of. So if you are having trouble locating a team, then make use of those resources. If you're having trouble finding your last team member, make use of those resources. And so that hopefully we don't have any awkward conversations after the names of team members is due and there's unpaired people that we have to sort of force to form groups together. So I like it a lot better if you choose your own groups, but if we have to, then I'll have to assign groups and we can do that. But as much as possible, try to meet up, at least have some introductions to people before you have to do a project with them. And again, I know group projects are not very popular, but you have to do so many of them, and this is one of the classes that sort of has been tagged as a good opportunity to do kind of a group project. And so it's just a standard part of this class, and so we all have to get through it. But you will, and you'll be really impressed with what you've got, and it's almost like a mini capstone. So hopefully that'll look like a better thing. It didn't sound like right now, I guess, but afterwards, looking back on it, hopefully it'll be a good experience. We'll be able to say, look, I modeled a real system using a computer simulation tool. I'm not expecting you to do as much work as a capstone, really. It's only a couple weeks of work. So there's the expectations are a lot lower than they would be for a capstone project, but you're supposed to practice doing this for more than what we just assigned for a homework assignment. So any questions about the schedule, agenda, administrative stuff moving forward? All right, so where we left last time, we were talking, we introduced input modeling more formally than we've done so far. I tried to sort of say, well, recall back in lab 6, I had you build this pipeline of, create block, 2 process blocks, and then a dispose block, and we just changed whether things arrived deterministically or stochastically in different parts, and hopefully you saw you got different results. And sort of, a simpler version of that, like if you think back to things if you've taken 470, you might be familiar with these queuing nodes, which we kind of group into these categories using this thing called Kendall's notation. So you have these things like MM1, DM1, MD1, MG1, and all of them look like this. Like if you were building them in Arena, they'd all look like a create block, a process block, and a dispose. So generally, they look like this, where you've got arrivals, a queue, and a service node. But what makes them different is what input models you put into these things. What are the distance between arrivals, the inter-arrival times? How long do they stay in processing? And you get major differences as you go from one to the other. So it just goes to show that the input models, even if you've got the structure of the system correct, if you've got the wrong input models, then you can get a totally different inference on what you should do in a system. So you might make a very bad recommendation, even if the system at this level looks correct. And so, input models for queuing are often these inter-arrival times and service times. For supply chains, typically we're modeling demand and lead time. So we've seen that in the Bucky example that you built in Lab 7, that you built twice in Lab 7. So in that case, demand and lead time were important things, but you saw that we could trickle in other input models as well, like how often the evaluator comes to visit or evaluates. Maybe it isn't every day. Maybe it's stochastic. Maybe sometimes it's every 2 days. Reliability problems, the input models are typically having to do with failures, so failure time. So there are some standard things you know that you're going to have to model, and then you sort of have to figure out what are the other things. So one of the things for your final project is you might sort of say to yourself, the system that I'm interested in, does it fall into one of these 3 categories? Is it really a queuing system that is it a queuing network that I'm working with? Is it a supply chain problem I'm working with? Or is it a reliability problem? Or is it some mixture of those? And if you can find your way to sort of project your problem into one of these 3 categories, then when you're looking for those input models, you know that, well, if it looks at all like a queuing model, I probably need to make sure I've got at least these things covered when I'm looking for those models that I need to do for my inputs. If it looks like supply chain, if somebody is checking an inventory and managing an inventory, I better have some grasp on demand and how long it's going to take to actually get the orders after I do the order. If it looks like something where I'm interested in quality or reliability, then how often things fail is probably an important thing. And then again, you can mix these. So these are the broad categories that a lot of input models fall into. Of course, there are more, but this is kind of a nice thing to start with, a good first order approximation of many of the systems that you'll simulate. And so getting these distributions right is more than half the battle. Yeah.
Question on inter-arrival times. Why would you not be interested also in the arrivals themselves, like the number of arrivals to a queue?
Well, so a lot of that will end up being output. So I mean, if you have the inter-arrival times, you have to sort of say, what can I simulate? And I guess I could simulate the number of arrivals. I could say that well, I'm going to simulate the next 10 minutes, but I'm going to do it all in one instant. And I know in 10 minutes, I'll get 50 arrivals. And that might depending on the simulation, maybe that's all you need. Maybe your simulation moves in blocks of 10 minutes. And as long as you know how many came in the 10 minutes, that's enough. But in most of these queuing models, you need higher resolution information. It really matters not that 50 came in the last 10 minutes, but that all 50 came in the last minute of the 10 minutes. So how bursty the traffic is often a key consideration in queuing models. So if it's spread across the whole interval or just clumped in one. And that's why the inter-arrival times often are more useful. Now, what I'll show you, either in this lecture or in the next one, is that when you're taking and actually we'll go into this in detail a little bit in the lab 8 as well, is that even though you'll need to simulate inter-arrival times in ARENA, it's a real pain to go out with a stopwatch and get inter-arrival distributions out in the real world. So in the real world, if you can make a Poisson process assumption, simply going out and counting arrivals in an interval actually will allow you to back calculate the inter-arrival time or the arrival rate. So even though you might simulate inter-arrival times, you might gather data on number of arrivals. And we'll go into that in detail in the lectures here, but that makes data collection much, much easier. And that's because of that fundamental relationship between the Poisson distribution and the exponential distribution. One's continuous and one's discrete, but they're related by the same parameter. And again, we'll get into that. All right, so the easy part of this input modeling is this hypothesis testing. If I say I think that my inter-arrivals or whatever come from this distribution, then we will learn how to generalize things like the KS test and the chi-squared test that we did pre-midterm in order to say, all right, well, here's data that I have from my real system, and does it match this? So I think this is how the data were generated. Does that match? Can I find support for this hypothesis? That's the sort of the easy part. The harder part is actually coming up with, well, here's some data. So what is the right hypothesis? And so that's kind of what we're focusing on today, is how do we isolate at least some families of probabilistic distributions that might go along with data that we've collected. And then we'll worry about parameterizing those families on Thursday. So how do we come up with those hypotheses? So this is the basic outline of this unit. We've talked about how to collect data from the real system. We're going to talk about how to identify these probabilistic families today, and then we'll do more quantitative work on Thursday on how you actually then say, fit parameters and then measure goodness of fit. And so let's get into that. So let's, this is an example I started last time about this metal detector, and I'm going to go in a little more detail so we can see how we implement this in Arena and how the process of collecting data will change our probabilistic models, which will end up changing what we do in Arena. And so let's see how that plays out. So just as a reminder, I said, well, let's say we have a metal detector. We've got entities that are the people going through the metal detector. The resources are the one metal detector. They all have to get through. So this is the bottleneck here. The activities include just the time it takes to pass through the metal detector. So relatively simple queuing network problem here. We've got arrivals and we've got a resource, and we're interested in how things line up. So inside Arena, I create an entity, maybe called people, and maybe I put a little picture on it, and I create a resource called metal detector, and I create a fixed capacity of 1. And then I'll show this diagrammed in a second, but just as a reminder of sort of the recipe here. And then in the flowchart modules, I then grab a create module to create those entities, so that'll be associated with people. And then I get a process that is configured as a seize, delay, release that will be associated with the metal detector. And the delay type is what I'm interested in building a model for. So how long do people walk through that metal detector? And then I draw a dispose, which collects the people have to go through the metal detector. And this is modeling them entering a building, let's say, but we don't care about what they do after they go through the metal detector, so we just get rid of them, we dispose them. And so this might be what it looks like. Very simple model, and I added a little visualization just to sort of emphasize you can have these visualizations in Arena that run in real time. So arrivals, process, and then the dispose. All right, so I got these, so these data tell me that after 1,000 real people, the mean and standard deviation are both nearly identical, and they're both about 30 seconds. Now, I know, based on my intuition about distributions, without thinking about my intuition of the real world, that an exponential gives me is a continuous distribution whose mean and standard deviation match. So, and I know that I frequently use exponentials to model interarrival times or service times. And so I might be tempted to just go into this model and put an exponential right here and say that's my service time distribution. It's an exponential with mean 30. But then I actually end up plotting that out. This is sort of the distribution of exponentials and kind of expected frequencies if I were to histogram that data. And I'd say, well, this is mean 30 is here for the exponential, but it's got this really sort of longer tail here. And so I do get a lot of arrivals that happen before 30 seconds, or services that happen before 30 seconds, but there's a whole bunch that happen later than that, some as many as almost 3 minutes. And there's just no way it takes 3 minutes to go through a metal detector. And so that gives me the insight that maybe this was a bad choice in my input model, because it just doesn't make physical sense. So always check your physical intuition after you've sort of processed it through your mathematical intuition. And then so, the punchline was from last time that when we actually look at the real data, we see it's bimodal. And so the real data have a peak that it sort of falls off, say 20 seconds or under, and then there's a secondary peak outside here. So do we remember what we sort of thought this secondary peak could have been about? Like what's happening here? Why would the real data look like this? Anybody remember the story from last time?
They have to go through the detector again.
Right, so they're right. I think I heard a couple of people mumble it, but the idea would be maybe these are the ones who go straight through on one pass. And then a couple of them get flagged, and then those people that get flagged end up being asked after they go through a special process. They either maybe have to go back through the metal detector, or maybe this is just modeling the time it takes for them to get a pat down or to have the wand go over them, and that's what takes a little bit longer. So we're actually seeing two populations that we thought we could model as one. So that tells us we have to change our Arena model because it's going to be very difficult for us to come up with one service time distribution that looks this way. You could conceivably take an empirical CDF for this, and then use like a cont or a disk to simulate this, but it would be better if we actually reconstructed this structure. Yeah.
So bottom line, the way you get those two distributions is by separating like the populations by special cases?
That's what we'll end up doing. Is we'll say everybody who's under 40 seconds, we're going to model that as one input model. Everybody who's over 40 seconds will be a second input model. So here's this. I could again use an empirical CDF, and I could use cont or disc in order to put that directly in that one there. But it kind of feels like, I feel like as an engineer, I want to know what's going on here. So I'd like to break this down into its constituent parts. So instead of doing it this way, I break things up here, so say by 40. So anything under 40 seconds, I'm going to put in one input model. Anything over that, I'm going to put in a different input model. And now I just need something in my model to decide whether an entity is in one population or another. And so now I've got these three things. I've got my long passage time distribution, my short passage time distribution, and my probability of being in one population or the other. And so I'm going to go back into Arena, and I'm going to drag a decide block in, and that decide block will be the thing that routes entities into one population or the other. And I'm going to draw another seize delay release that is going to be, say, associated, in this case, I'm associated with a metal detector resource, but you could imagine a second resource called like, secondary screener or something like that. But in this case, I'm just saying they're routed right back through the same metal detector. And then another dispose block to collect these people after this new process. So this is what it ends up looking like here. They arrive the same way. Some of them go through, some of them go through this quick entrance. So you can picture them sort of saying, are you in the population that's going to get detected? So it's a little weird. I model this with this decide block actually before the metal detector, just because that makes the logic flow better. So you sort of say, like, ahead of time, are you someone who forgets to take off their shoes or something like that? And so you're almost sort of assigning an attribute to these sort of people that come through. So if you're a troublesome person, then you go through the top branch. Otherwise, you go through the bottom branch. And for right now, behind the scenes, what we don't see is that these two processes use the same resource, which means if anybody is at walkthrough, then they queue up and get checked and vice versa. But I could have created two separate resources for that. Just for simplicity, I made them assigned to the same resource, as if they're cycling back through the same metal detector. And then I've got these two dispose blocks, and that just allows me to collect stats. And so I can see that at this point in the sim, 2 went directly through, or 2 got delayed, got checked, and 18 went directly through. All right, so now I just need to end up putting input models into these three blocks. And so I can say, well, I knew what these distributions, so if I go back to my two distributions here, I could fit maybe an exponential here, maybe a normal distribution here. Why is it normal? We may not have physical intuition for that, or you might say it might be normal because this process involves summing over lots of little steps, and that's why it might be normally distributed. But we have these two distributions we put in there. The probability of triggering the detector, we could go back and look at the data and say, well, I know that there's maybe there were 500 entities total, or 500 real people that went through, and this peak represented, say, 700 or 70% of them, and this peak represented the other 30% of them. And so in that case, I can say, well, then there is a 30% chance of landing in this population. So by looking at these two modes, I can actually estimate the probability of going into one population or the other. And so I can fully parameterize this model. And once I've done that, then I can start experimenting. And I can say, is it worthwhile to put a sign up here that says everyone must take off their shoes? How much would putting that sign up there make a difference? Maybe I need to pay someone to stand there and tell people to take off their shoes. But now I have to pay them salary. So how much is it worth it for me to pay them extra salary just to speed up this process? And that allows, this sort of are these what-if scenarios. What if I could get the probability of detection down to 10%? This is what the service time distribution would look like. What if I totally give up on this and now I've got a probability of detection of 90% because nobody does the sort of stuff they're supposed to do before they go through the metal detector. At that point, I pretty much just have one big peak over here. And maybe right now it's at 50%. So I can study these what-if scenarios, and then maybe there are metrics that I can apply to this and say, you know, this improvement is worth so many dollars. And then I can ask, is that dollar improvement worth the salary that I need to pay to help ensure that this detection probability stays at 10%? So those are the types of games that we can play with this. But the big thing that I was trying to drive home here is how seeing this distribution changed the way that we looked at the arena model, so that we built a totally new arena model with slightly different input models. Now with that in mind, imagine if I actually saw this distribution. So instead of seeing this bimodal distribution from back here, I saw a multimodal distribution that kind of has this harmonic series sort of thing going on where it keeps getting smaller and smaller and smaller and smaller with every peak. What do you think's happening there? Take 30 seconds and talk to your neighbor and sort of figure out, what do you think might have generated this funny looking distribution of data? Go ahead and chat. Remember, it's a metal detector.
Or maybe
All right, so anybody have any ideas? What is a physical process through a metal detector that might generate data that look like this? If I'm only keeping track, remember, so basically somebody enters the metal detector and I wait until they enter the building. And I see that some people enter quickly and other people take a really long amount of time, but there seem to be these distinct clusters of groups that some, take, a very short amount of time, then there's another group that takes the next mean, another group takes the next, and so on and so forth. So what would create these clusters in a metal detector configuration? Yeah.
reasons to set it off, so laptops in bags, metal in the body.
So that's one good hypothesis, is that it may be that, but like before, I had two clumps. And one clump were the people who forgot to take off their shoes, and the other clump were the people who very quickly, they were sort of prepared for the metal detector, and they were able to go through quickly. And it's possible that maybe all I'm seeing here is that there's some people that have they can kind of fix their issue very quickly, and others need longer times to fix that, and so on and so forth. But when I look at this, and I think that's a perfectly reasonable thing to model, then we would go back to the system and we'd actually inspect that. And we'd say, are there commonalities in this group? Like, do we notice that maybe this is the group that has like the metal hip or something like that, and they can do a wand over them and it takes really quickly. But maybe this is the guy who keeps forgetting that he has another pocket. And so, he like takes out his keys and then goes through and he takes out his phone or something like that, and it just takes a really long amount of time. So we would have to go back and inspect that. So let's put that hypothesis as on one side. Is there an alternative hypothesis that might have also been able to generate this? Yeah.
Say like the far left one's like, there's like different lanes, so it's like one's like pre-check, one's.
So that's another interesting hypothesis. I think also worthwhile alternative that we would have to go back and re-look at the system to see how it's set up. But it could be that, yeah, we have multiple lanes, and this just, for some reason, one lane is a lot slower than the next one, and there's this sort of natural ordering where, there's always going to be an ordering because there's always going to be one lane that's fastest and the next one that's maybe a little slower, and this is just how it shakes out. So we should put that up as another hypothesis that we'll need to maybe go back and gather more data to see. Is there any other possible explanation? Yeah.
Sometimes the machine is slower at detecting.
It could be, so that sometimes, but then like the fact that there are these gaps, and these gaps are so regular, is something that I think is peculiar. How would we explain this regularity in the gap between these groups? Yeah.
It'd be like random
Well, yeah, so you could say that, but then again, like, if it's like a random thing, then would you expect, I mean, these gaps are in time, so that, like, it's like I think it's like every 60 seconds or something like that. So why would I have, like, some people delayed 60 seconds and some people like 120?
It's like sometimes they just like do like a pat down, sometimes they do like your palm, sometimes they like take you to another area and do like an increase.
Sure.
So that like that'd be 4 different processes.
That's true, and I think that's another, it's a third, but then would it make like it might just be coincidence that like the palm is 60 seconds and then going to the other room is 120. The fact these are all separated by roughly 60 seconds seems weird to me. Yeah.
What if they like run out of bins at like a certain amount of capacity and then like they have to redistribute bins or something that people can put their stuff in?
That's kind of an interesting idea, and maybe that would generate something like this, is that, you know, the first time they run out of bins, like usually they can get you the bins back, but occasionally, and due to some weird discretization with the number of bins, you either get into a short delay or a moderate delay and all those sorts of things. Yeah.
Maybe it's the difference in the time studies taken from the people. So multiple people are taking 5 studies, and they're all doing it slightly different.
There could be a data collection error here too, sure. Again, the 60 seconds is a little weird. Let's move on, but I think we can come up with a lot of different, this is exactly the way I want you to look at your data, and when you see peculiarities in this, then that tells you that you need to model those peculiarities, and we've just heard at least 4 different ways that you could model this. Now, before you pick one of those and go with them, you would need to go back to the system and confirm that your idea of how the system is structured is actually how it's structured. So, yeah, question?
Yeah, going back a little bit like with bimodal distributions and how you separate that into like these 2 process blocks, could you also do like a loop at the side block and then just keep one distribution as opposed to having to separate into 2?
Yeah, hold that thought for just a second, because that'll be very relevant in a second here.
Okay.
Yeah, so with that sort of idea that about separating these things out, I could do like what I did before and separate out just this little group and then see what else is left over. And that basically then forms what looks to be an exponential distribution of those with the short times, but then still this weird peaky thing, multimodal thing for everything that's left over. So what I might then do is I might notice that if I actually look at every peak, then so this is the first peak, and this is, so I'm going to look at this peak here and this peak down here. And so this is the first peak here, and this is that other peak down here, like, you know, there was 2 down from it. And there's a lot less data here because the frequencies were a lot less then, but roughly the standard deviation is about the same. These 2 distributions look roughly similar to me. So it's almost as if what's happening here is I'm getting this distribution with fewer people repeated 60 seconds later, and then repeated with fewer people 60 seconds later, and so on. So one alternative way that I could get something like that might just be, what if people run through the metal detector multiple times? And if that's what's actually happening, then all I need is sort of a get-checked distribution, which is sort of this normal distribution. And if it sort of dominates this walkthrough distribution, then this could generate that same data. So the idea is I get arrivals that come in, they walk through a metal detector, and then, so they all pay that cost. And then if they get detected, then they go through again, and there's a chance they'll get detected again, and again, and again, whereas eventually some of them will get out. But there is still some chance that somebody could be trapped in here forever, at least in this model. And this model right here, you actually can use to generate data that look like this. Now, whether this is a good model or not, I mean, this is probably not totally realistic, but it is at least, you know, there are definitely metal detectors that operate in a very similar way like this. Now, most likely, you would keep track of how many times people went through. If they've gone through the metal detector more than twice, then maybe you'd shoot them off to a different process rather than gunking up the metal detector. You might prioritize them, so you can build a priority queue here. So I ran actually a summer workshop for undergrads modeling airport processes where they built something like this, and it was actually one of their kind of homework problems was to set this up so that there was an increasing probability based on the amount of times through the system that they got sort of moved, had first access to the metal detector, and that may also affect these distributions. But this is at least a fifth hypothesis for what might generate those multimodal peaks. And I'm not saying this is right or wrong. We don't know that without knowing the actual system. But I at least want you to get in the practice of going out, taking these data, and then saying, this is a weird structure, and it's so regular that this indicates that how I might have to redraw my system. So we talked about how we start out with these things and we cluster our problems into these very basic problems. Like this problem is a queuing theory problem, a queuing network problem. With any queuing network problem, this is probably a structure that I'm going to see at least once in my model. So I start here without knowing anything more, and then I go on and I look at my data, and my data do not look like a normal service distribution, which changes my queuing network. So now my queuing network has more nodes in it. And then I look at my data a little more in detail, and let's say it looks like that, and I use the data to tell me how to change my queuing network. So we go back and forth between a hypothetical model and the structure in the data, and then update the hypothetical model to better reflect the structure in the data. And in the end, it makes it simpler for me, because now instead of having to find some weird distribution that looks like this, all I need are two distributions, an exponential and, say, a normal. And with the right structure, then I put the exponential here, the normal here, and then I maybe validate this and see that this definitely can produce data that look like this. And if it does, then I feel like this captures the salient features of my system. So there are questions about this kind of example of how you might go through starting this process. Yeah.
Were those histograms like historical data, or were they data from the model?
Well, so yeah, these histograms here, I did it. So I mean, basically, because I was looking for, I was cooking up an example. I basically, built the model first, and then took data out of that model, and then I told the story the other way around. So, I kind of knew that this was a possibility because I took the data out of this. But in principle, these data could have been data that were taken from a real system. And I could have then built this thing and then ran this thing and found that it generates something that looks totally different, in which case I say, well, I'm missing something. Any other questions? All right, so today we're focusing on, speaking of histograms, now that you've taken data from the real system, then how do we go about using these histograms to build up physical intuition, or combined with our physical intuition of the process, and a few kind of qualitative/quantitative methods to come up with, at least at the simplest level of exponential, Poisson, etc., the right distribution. So once you've finally broken things up into the point where you're pretty confident that you've got something that is a service time distribution, now how do you decide what service time distribution to use inside that block? That's what we're focusing on now. So histograms are a great way to start with this, and so hopefully you've been using histograms more in other data-driven classes. For samples of continuous data, they give us an empirical PDF. For discrete data, an empirical PMF. The big issue with histograms is how to choose those bin sizes or class intervals. And so it really depends on the number of observations and how dispersed, how varied the data are. And a good suggestion is for continuous data, you can take the square root of the sample size. But really be careful. If you know that it's discrete data, it's always best to bin every outcome separately. You don't want to bin across outcomes, because then sometimes the histogram can make it seem like you have discrete outcomes that don't actually exist. So if your outcomes are 1 and 2, then you might bin those together, and the middle of that bin might be 1.5, and you might think then your outcome's 1.5, but you've just managed to hide 2 outcomes, find an outcome that doesn't actually happen. So it's good for discrete data to just bin them separately, regardless of how small those bins are. But for continuous data, it's a heuristic, so it's difficult. So like if here's continuous data, this is the same set of continuous data, just binned with different bin sizes. And so it's almost like you just know it when you see it, what's the right bin size. So here, this is too refined. I can't really tell what structure is there. Here it's too coarse. I mean, this almost looks like a uniform distribution. But finally, here, it's the kind of happy medium where I can kind of tell that, okay, I do sort of see some shape there. It smooths over some of this mess, but it doesn't smooth it over so much that it totally disappears. And so that's kind of what you're looking for, but there's no objective way that I can tell you that exactly how, for every data set, exactly these are the bins that you're going to want to use. Fortunately, now you don't have to do a lot of these bin choices yourself because there are good heuristics built into things like Excel, MATLAB, R, etc. But you should keep in mind that they're just using heuristics. And so you should always feel free to scrutinize the choices they make before you end up making an important decision, which might you did happen to bin them a little too coarsely, and you ended up deciding that this is a totally wrong structure. So double check by re-binning, but on your first shot, usually what comes out of Excel is probably okay. Now, if it's discrete data, then like this one here, by discrete data, I mean the outcomes are arrivals per period, and the frequency are how many we observe. So in how many times do we get 0 arrivals? Well, that happened 12 times. So there were 12 periods that had 0 arrivals. And there were one interval that had 11 arrivals. But like most of the intervals happened, or the outcome that was most frequent was in a time period to get 2 arrivals, and that happened in 19 of the time periods referenced. So here I have discrete data, and so I want my histogram to be centered on every outcome. And so that's kind of the 2 rules. Now, can anybody recognize this distribution? It's a discrete distribution, and it's a popular one. Any guesses? You don't know a lot of discrete distributions, so and it's arrivals per period. Poisson, right. So whenever you think, again, queuing that works, whenever you hear arrivals per period, a good null hypothesis is the Poisson, and then find reasons to reject it later. But you can always start with Poisson, and that's what that one is, the Poisson distribution there. Now, once you've picked a distribution, if let's say you need sort of to jog your memory on what distributions are available, or you don't remember how to implement it in Arena, you go to the Tools menu in Arena, go down to Expression Builder. Then in the Expression Builder, there's a whole section on random distributions. And underneath it, it lists every distribution that Arena can sample from without any extra work. And so if you click on one of those, it will even then update over here and tell you what the parameters should be. You fill in those parameters, and it gives you an expression down here that you can copy and paste into that process block for that service time distribution. So this is a really useful tool. It's, I think, a lot of times more useful than Googling for help on, what is the log normal syntax in Arena. We'll just go into the expression builder, click on log normal, and then it'll give you extended descriptions of what the arguments are, and then it'll make the expression for you after you've filled it in. So remember that's there. It's super useful. So then after you've got these choices here, so you've got maybe a bunch of possibilities. Well, then how do you refine that? And so you want to ask more about the context and physical properties. And so is it discrete or continuous? That's always the first question to ask. If it's continuous, is it bounded? So you've noticed the exponential never goes negative, but the normal does. So it's sort of bounded on one side, but not the other. Are there other features? Do you have an insight that it's memoryless? And so if it is an inter-arrival time distribution, and you don't think that one arrival gives you any information about the next arrival, those are independent inter-arrivals, and that gives you an idea that maybe it's an exponential. Maybe I'm looking at a memoryless process. Am I looking at a process that's additive? So I mentioned that maybe if someone's going through a process of after they get flagged by a metal detector, they have to go through a lot of sub-processes. They have to take out things out of every pocket, and they have to maybe take off their shoes, and they have to do these. And if you imagine each one of these has a little distribution, and I'm adding up 8 of them together, then probably that sum is going to look bell-shaped, and it's probably going to be approximated by a normal. Is it correlated with other processes in the system? We talked about that last time. And then so I get kind of some intuition about where I should look, and then I look at the shape of the histogram, and hopefully refine that even further. And we're never going to have a perfect model. Stochastic modeling necessarily leaves stuff out, but we want to get a good and illuminating approximation. So the frequently encountered distributions, on the analytical side, if you have insight into physical processes that are going on, exponential, normal, Poisson. On the heuristic side, so those of you who are working on the Rockwell project, the ARENA project, the competition project, they've given a bunch of heuristics like we know that this particular shipping time doesn't ever go less than this or more than this, and it's most likely this. But that's all they've given you. Well, that tells me that maybe a triangular is a good distribution for that. So these are more, they're not based on physical insight, they're just based on the best you can do with the data you've been given. So lecture 2, we went over that, and we'll review that just a little bit here in a second. But so the first big thing, is it discrete or continuous? So how many people say that this is the discrete distribution? How many people say that this is the discrete distribution? So this is the discrete distribution. We know that, and we'll go over this a lot more in Lab 8, but because there's giant gaps between the outcomes. There's no gaps between the outcomes here, so it probably has a continuous range of outcomes. So continuous versus discrete. I can also look at the empirical CDFs, and if the empirical CDFs have giant steps, it's probably discrete, but if they're nice and smooth, it's probably continuous. So that immediately eliminates a huge number of possibilities once you've definitely honed in on this has got to be a discrete distribution. So, once you've got discrete, and we've talked about a bunch of these already. We've also talked a bunch of continuous already, and then there's a bunch more that you'll gradually get more intuition about over time. But if worse comes to worse, then ARENA provides these data-driven last resorts. So on the discrete side, there's that disk function where you basically can take that empirical CDF and encode it as the arguments. And then on the continuous side, you can effectively sort of approximate these data as they're discrete and then interpolate between the outcomes, and that's what the const does. And so the syntax is identical to discrete, it just connects adjacent outcomes in the CDF with straight lines. And so these are your data-driven last resorts if you really can't find anything. But hopefully you can find something, because it's always better to boil your data down to a couple of parameters than to use the data directly, because there might be outcomes that you haven't observed that are not really captured in your data, but they will be captured in these models that you can find up here. And so I'm just going to go over 4 of these that are the common ones, just as a reminder. Norm, implemented in ARENA this way, is the second parameter of standard deviation. Every program does this a little different. Some ask for variance, some ask for standard deviation. We typically specify it mathematically with variance here, it's the symmetric distribution. So what's interesting about it? It's additive processes, like I just mentioned. If you've got something that you're measuring from time A to time B, and there's a bunch of sub-processes in between that get added together, then it's not surprising that you'll get a symmetric distribution, and you might be able to model it really well by a normal. So again, think additive, normal. The exponential, so this is the classic interarrival time distribution, also sometimes service time distribution. If somebody tells you that it's non-negative and it's got a mean, this is your best guess. So if all you know, the average and that it's non-negative, nothing else, then the exponential is always the most sort of unbiased choice. So it's always positive, it's memoryless, it has this funny feature that its mean is equal to its standard deviation. It's got only a single parameter. So if there are 2 distributions that both look kind of exponential, they both have a similar fit, but you can fit it with the exponential, it's better to choose the exponential because it might use less parameters than the other one. It's always better to use fewer parameters in a model than more because you don't want to overfit your data. But if you do need more flexibility, the Weibull is meant to be a flexible exponential. If you say it looks kind of exponential, but it kind of screws up at the early points or at the late points, then the Weibull is nice because it's basically an exponential with what we're calling a shape parameter. And so it basically takes an exponential, and on that shape parameter, it might pull down this to sort of turn it into something that has a hump in the middle of it, or it might stretch this out to sort of make it kind of even more peaky on one side. So the scale parameter of the Weibull is meant to be like the exponential scale parameter, but the shape parameter deforms it a bit. And so the Weibull is often used by reliability people because they often model products that are approximately exponential in some part of their life, but eventually kind of give up their ghost. So they might die late or die early. And so if they have a burn-in period, you just got to get through, and then they're exponential. Then we've got a Weibull where maybe they have early failures. Or if they pretty much have a constant failure rate, and then eventually, once they reach like 5 years of life, they just immediately die, then actually you can say, well, all right, we'll actually fit that with a Weibull, where we're going to cluster most of the failures way late. And so it's a way to sort of take your intuition of the exponential and just massage it a bit to turn it into the more realistic distribution. The other related distribution is the Poisson distribution, which is, keep in mind, people always get these confused. It's discrete. It is the count of arrivals whose inter-arrivals are exponentially distributed. And this, as I'm going to show you an example in a second, makes collecting inter-arrival time data so much simpler because you can count people instead of counting times between them. So we'll see that here in a second. Are there any questions about those distributions? Those again, there's a bunch more, but I just wanted to remind you of those four. All right, so this again applies to the data here. So here's a Poisson distribution from before. Now, if you remember your physical intuition about the mean, if I wanted to figure out an estimate of the Poisson parameter, there's a single parameter for the Poisson, we call it alpha. It is equal to the mean of the Poisson. Now, can anybody guess, the mean of this distribution? How many people think the mean is over here? How many people think the mean is here? So as I slide my hand from here over to here, raise your hand when you think I've hit the mean. All right, put it there, and then put it down when you think, all right, so it's around here. That's pretty good. That I think the mean of this distribution is actually a little bit more over here. I think when I took the mean of these data, I think it was actually just a little bit over here, but I think pretty here is pretty good. The intuition you should have, though, is, again, remember, if these were blocks that were weighted by their height here, that are sitting on a teeter-totter, where would you put that fulcrum to keep it balanced? And so if you have that intuition, then when you stare at a histogram like this, even without taking the data, you can get a quick back-of-the-envelope estimate of your input model just by guessing the mean for this one here. So the reason that you might use these Poisson is, let's say I've got, so these are data that I've taken, Poisson data that I've taken that have a mean of 49.9, so it's right there in the middle, and it's very hump-shaped here. And so it should be not surprising that Poissons at very high means look symmetric, because a count is kind of necessarily additive. Like, how do you count? You add one to the previous count. So not surprisingly, Poisson distributions look more and more like a normal the higher these alphas get, the higher these parameters get. Now I've gone out and I've basically said, I've taken a bunch of 10-minute periods, and I've counted the number of arrivals that occurred in my 10-minute period. So that was much, much easier than me counting the time between every arrival. Because I can just sit there and watch how many times people enter a restaurant, for example. I don't have to actually have a stopwatch and say, all right, between those two arrivals, here's this time. Between those two arrivals, here's this time. Or I don't have to actually say, all right, she arrived at this time, he arrived at this time, and then in a spreadsheet later subtract them. I could just count and say, in these 10 minutes, I got 2 arrivals. In these 10 minutes, I got 5 arrivals, and so on. And so I get this data right here. That was much, much easier. But the question is, how do I then build an exponential model like that I want to simulate in ARENA? And so it turns out that after fitting this Poisson parameter alpha, there is a direct translation to get that lambda parameter out for your exponential. And the way it works is I can take alpha, which is this sort of thing here, and divide it by the length of my interval. So if I want to know lambda, which is units of per second units, arrivals per second, and I know arrivals per 10 minutes, if I just divide arrivals per 10 minutes by however many seconds are in 10 minutes, I will get arrivals per second. So that 50 arrivals per 10 minutes, which comes out here, corresponds to 0.08 arrivals per second. So not many arrivals per second. But these data here in this blue, this is actually the same data that I see from over here. So basically, if I were to look at those arrivals and count however many arrivals occurred every 10-minute interval, I would get this histogram. But if I looked at the in-arrival times, I would get this histogram. But this red fit comes not from me estimating the best exponential. It actually comes from me estimating the best Poisson and then inferring the exponential parameter from the Poisson. So even if you want to simulate exponential interarrivals in your simulation, you don't have to take exponential data. You can take Poisson data and divide by your interval length, and you'll end up getting a really nice fitting exponential. So that makes data collection much, much, much easier. And you'll have more practice at that in the lab. Yeah?
In the Poisson distribution, the alpha represent that 50 is like the mean of 10, like a bunch of 10.
That's right. That's right.
And then in the exponential, the lambda represent.
The lambda in the exponential is, well, it's easier to think of what 1 over lambda is. So 1 over lambda is the mean time between arrivals. So there is 12 seconds on average between every arrival. So there are 50 arrivals in every 10 minutes. And so not surprisingly, there's about 12 seconds between every arrival. So that's basically, that's one way to go to the other. So it's going to be much nicer to simulate exponentials, but it's a bear to deal with exponentials in reality, so deal with Poissons in reality. But once you have Poissons, then you can get the exponentials back with a simple division. All right. So any other questions about that? Yeah.
I mean, is it okay to do that if we know that our process is Poisson, like if we know lots of groups are coming in and stuff like that, can we still do that?
That's a good point. And so we'll go over this more in the lab presentation, but the basic assumption here that I'm making is that I am counting these over a period of time where I do think the arrivals are exponentially distributed. So like these might be the counts that I take for every 9 a.m. Monday, Tuesday, Wednesday, Thursday, and Friday. Now for 10 a.m. I need to do this totally differently. For 11 a.m. totally differently. But I think from 9 to 10, I can pretty much assume a constant arrival rate. Does that make sense? So yeah. All right. So that's a great example. If you're modeling a bank or whatever, you might just say, we're going to model 9 a.m. to 10 a.m. at a bank. So you go out to the bank Monday through Friday, and you get counts every 10-minute interval. Monday, so you only get 6 of them on Monday. You only get 6 of them on Tuesday, and so on. But you take all of those together, those 30 arrivals, and then you can estimate a nice Poisson. And then from that Poisson, you can then estimate a nice exponential. And then you can simulate the exponential in ARENA, even though you measure the Poisson in real life. Okay. All right, so there's a bunch of other distributions, and I've kind of made a cheat sheet here that where I've kind of had a one-line reason why you might choose that distribution, and I've also added, where possible, simple ARENA expressions for each one of these that you could use to draw samples from those. So I'm not going to go through all those, but that's there in case you sort of want to say like, well, I'm not quite sure what this is. Like, if I want to build some intuition for why I might use this one over this one, or I just need a reminder of how an Erlang differs from a Weibull, then those are all there. So just added those in here. And then also a reminder that, again, at the last resort, you can use dist or cont with your raw data. Or, and this is something that the input analyzer will do for you automatically, you can actually use a histogram to use as the arguments for the disk and cons. And so you don't actually have to use the raw data. If it's a continuous distribution, you can generate a histogram that has 10 bins. So you might have collected 1,000 data points. And it would be crazy for you to put 2,000 arguments, 2 per data point, inside a single cont in Arena. But in the input analyzer, you might take those 1,000 data points and turn them into a histogram with 10 bins. Well, then the frequencies of corresponding to each of those 10 bins will end up being something that you can put inside here. And that's actually what the input analyzer does for you automatically. So if you ask the input analyzer to fit a disk or a cont for you, it'll do that based on the histogram, not based on the real data. So that makes it much simpler when you take a lot of data, but you still can't figure out what basic model to use. You can still use this as a last resort without having a gigantic expression string. All right. So one thing I will say going into the lab, be very careful in your input models. The input analyzer will always want to fit things like the gamma and the Weibel because they are very, very flexible distributions. But if you have insight that you're like, it looks at it and you say, it looks just like an exponential, and the exponential has just as like the sum of squared errors that comes up in the Arena input analyzer is almost the same as the gamma. The gamma is only a little bit better. It's always better to use the distribution with fewer parameters, especially if you have physical intuition. You may not have any physical intuition as to why it would be a gamma distribution, but if you have a lot of physical intuition as to why it would be an exponential, then just go with the exponential. That'll be much easier to defend. And then you can evaluate the goodness of fit of the exponential, and it may not be that much worse than the gamma. So the thing that has the absolute best goodness of fit is not necessarily the best model to use, especially if it has more parameters than something with a similar goodness of fit, but just a single parameter. So that's something that I always see that when people present their final projects. They'll just pick what other distribution that the input analyzer gives them, but that is always like it's really dangerous because you end up overfitting your data and you end up avoiding models that make sense for models that just sort of the numerics worked out better. All right, so wrapping up here. So the idea is I've now, let's say you said I'm not sure if it's an Erlang or a Weibel or an exponential. How do I get more insight? Because to me, visually, they all look roughly the same. And that's where we start with probability plots, these so-called plots that some of you may have heard of this term fat pencil tests, especially if you've had old, much older faculty than me teaching you, then they probably bring up these fat pencil tests. No one younger than me would ever use this term, so it's like a shibboleth as to how old your instructor is. So how many people have heard this term, fat pencil test? All right, old faculty. So nowadays so it's funny, like if you look at the Minitab, of course nobody uses Minitab anymore either, but if you look at the Minitab documentation, they actually even make jokes about the fat pencil test where they say well, if you happen to be out of electricity, you can use the fat pencil test or something like that. So, I mean, even among the people who use Minitab, fat pencil tests are archaic. But this is where the fat pencil tests come from. And so the idea is if you sort your data, you can graphically evaluate them using either a QQ plot or a PP plot. And you actually you do one and then you follow with the other. And it's a way to visually interpret how good these fits are. And so the QQ plot is basically going to compare inverse CDFs between your hypothetical and your actual. And then the PP plot compares CDFs. And there's a reason why you would want to do inverse CDFs for one and CDFs for the other. So let's see how that works real quick. So QQ plot, basic idea, sort my data. And I have a hypothetical distribution. Let's say I've got the inverse CDF of an exponential, and or something like that. And so I can then use the rank in my sorting as a kind of faux probability that I can plug into the inverse CDF, and it will then sort of tell me that based on where your data point falls in the rank, here's the data point I kind of expected you to draw if it really came from this distribution. and then you look for a linear relationship between them. So here's an example here where I actually drew data from a normal with a mean of 5 and a standard or a variance of 9. And then I used a hypothetical standard normal. So the mean and variance are totally different. But when I plot them on the QQ plot, they land right on this line. And that line indicates that it's probably a pretty good fit. Yeah, question?
Could you repeat what QQ plot stands for?
Oh, sorry, the Q is short for quantile. And a quantile is just another name for inverse CDF. So, so this is where the fat pencil test, if you laid a fat pencil on top of it, it would cover all the points. So it's a good fit. And so, but I could say, well, what if I did data from an exponential, but I plotted it against a hypothetical standard normal, and then I get something that a fat pencil couldn't cover, and so it's a bad fit. And so what you should do in this case, rather than just saying it's a bad fit, is you analyze how it's a bad fit. And I put kind of a set of recipes here. And so like if it's a line all but a few points, then that's okay, those are just outliers. And then there's this kind of pairing here where if the left end is below the line, but the right end is above the line, then you've got long tails at both ends of the distribution. Otherwise, your data is sort of overexpressed relative to your hypothesis in the extremes. So you should go out and find a hypothesis that has more representation in the extremes. If it's the other way, where the left end is above and the right is below, then that means that it's not as much expression at the extremes as your hypothesis. So you should find a narrower hypothesis. If there's a curved pattern, so this is where this comes into place. This is a curved pattern with decreasing slope. So a curved pattern with slope decreasing tells me that I've got some skew to my data, which tells me that the data are skewed more than so in this case, my data here, exponential, they don't exist for negatives, but they exist for all of the positives. And that is far more skew than a standard norm. So that tells me that I need to find something that has the appropriate skew. So I need to take my norm and look for something more asymmetric. So these recipes all kind of tell you, relative to your hypothesis, where should you move? What other family should you move to? And that kind of gives you a quick an idea there. Once you get good agreement in your QQ plot, you move to the PP plot. The PP plot plots, you sort the data, but now you're going to plot the rank against the expected rank. So I've sorted my data, and over here it's just I, which is the rank, minus 0.5 just for continuity, divided by n to make it between 0 and 1. And then I plot that against my hypothetical CDF evaluated at the data point that is that point in the rank. And so this sort of tells me, here's the quantile it's in, here's the quantile we expect it to be in. It's really closely related to like a Kolmogorov-Smirnov test. So here's an example. I've got data in the blue bars. I've got two hypotheses. So by I can't tell the difference between the gamma distribution and the normal distribution. They both look like they're pretty good fits. So which family do I pick? If I go to the QQ plot, it's not that helpful because both of them sort of pass the fat pencil test. There's no real difference between this green and the red and the diagonal. They both look like they agree. But if I go to the PP plot, then I see the red one lies right on top of this line, but the green one has got more deviation here. So there's actually daylight between these two. So that tells me that the red, the gamma, is probably a better fit. And that's actually good because the data that I drew from is actually from a gamma distribution. So that's generally the process that you follow. You start with a QQ plot, you look for these lines, and the QQ plot mainly is focused on how well the tails agree. And then after that, if you get agreement in the QQ plot, then you go to the PP plot. And the PP plot really focuses more on the middle section where the mode is of the distribution. If you start with a PP plot, they almost always will not agree if they're way off. They have to sort of have a minimal level of agreement for you to even start with a PP plot. And that's why you had to do the QQ and then the PP. And then then you can discriminate from there. And then again, the PP plots are uninformative unless you do the QQ first. So any questions about that, this graphical evaluation? They're very often used. If any of you go into industrial statistics and do a lot of linear modeling, you'll often need to guarantee that your residuals are normally distributed. And the common way to do that is to take your residuals and put them on a QQ plot relative to a norm and see if they fall in a line. And if they do, then that's often your first step that you probably can keep going ahead with your statistics. We'll talk about more quantitative stuff next time. But again, any more questions about how to apply what I mean by the QQ plot and the PP plot? Quantile, quantile, and probability, probability. All right, so we've talked about collecting data. We've talked about looking at the data. If you want to see more advanced versions of that, then other than a histogram, a nice substitute is kernel density estimation. So a lot of software tools will give you that option now. We've been focusing on PP plots and QQ plots today, but if you take a reliability course, you'll probably talk about Weibull plots, which are very similar, but they're focused on the Weibull distribution, zip plots. Sometimes if you've got exponential or power law distributed and you want to tell the difference, you use semi-logs or log logs. So plotting the data is often your first step in figuring out what the heck's going on. Next Thursday, or this Thursday, we're going to then actually go into the more quantitative. How do I pick that parameter, the best parameter? And then once I've picked it, how do I evaluate goodness of fit? We're going to revisit chi-squared and the KS test, but I'm also going to introduce you to Anderson, Darling, and Shapiro-Wilks, and we'll talk about p-values. So I'll have some questions that lead up the first part of the lecture, asking you guys to chat with each other about how much you remember about type 1 error, p-values, and so on, so that we can kind of figure out how it's going to apply to this. And those of you who think you know your stuff, I'm hoping to challenge you. So you're like, I know alpha, and I'm done with alpha. I'll never need alpha again. Well, I will give you alpha back. Any questions? All right, well then let's do an attendance exercise. And so my question to you is, if you took the retake, did your score go up? Just kind of. If you didn't, say NA.
What was the question? Sorry.
If you took the midterm retake, did your score go up? Yes or no? And if you didn't, just say NA.